Okay, hopeful. I'm going to be honest, this is the second time I've done this because I'm not sure what I'm doing here, so let's hope this works. If it's not working, text me. Here's a set of notes that you should have in front of you to start this lesson. I'm going to switch the screen so all you can see is the screen, so you won't see me unless I flip it back. So don't freak out when it just goes to notes. I didn't go anywhere.
When you hit start streaming, did it show your face on the second screen?
No.
Okay. Continue and we'll see how it rolls.
Continue.
Okay, we'll see how it rolls. Alright, so acids and bases. This is something that should be a review to you, especially if you had me last year for pre-AP chemistry. You did a whole acid-base project. So let's go over the basics. What's something you think of when you think of an acid? Vinegar. Lemon juice. Orange juice. Okay, those are things that we all think of as being acidic. And so the word acid comes from the word meaning sour. So you should think of something like a lemon when you think of something that is sour. Okay? Alkali is another word that we'll use for base. Okay, so you'll see the word basic or base or alkali or alkaline. It is all the same, and they'll use it interchangeably. Okay? All right, so what's something you think of when you think of a base? Soap. Lye. Milk. Right. Bleach. Okay? And something like baking soda. Baking soda is a common base that we use. And bases feel slippery and their taste is considered to be bitter. So anything that's really slippery, like soap, or anything that would taste bitter, like I don't know if you've ever had the pleasure of tasting baking soda, but it is very bitter. It's very nasty. It's not a good taste. All right? Yeah, toothpaste, like when you brush your teeth with it, okay? Toothpaste has a better bitter taste because it's got a lot of bases in there, all right? So we use them in everyday life, so we come in contact with them often. There are 3 different definitions you can use for acids and bases, all right? The main one we're going to use is the Bronsted-Lowry, that second one. So that's the one you really need to concentrate on, but we are going to go over all 3 of them, just so you are aware of what they are, because we'll use all 3 definitions at some point in time. So an Arrhenius definition is for the first one. For an acid, it donates a hydrogen ion in water. Okay, so donate would be like when you donate something, you're doing what with it? Giving it away. Okay, so in this case, we're going to donate an H+ ion when it's in water. A base is going to donate a hydroxide ion in water, which is OH negative. Okay, one of the key things that you need to look for when you're trying to decide if something is an acid or a base is you look for hydrogen for it to be an acid, and you look for hydroxide for it to be a base. So anytime you see anything that's bonded to hydroxide, you know it's a base. And anything that starts with a hydrogen, like HCl, I know that's hydrochloric acid. How do I know that's an acid? Just by looking at the formula HCl.
H starts with H.
Because it starts with H. That's from last year. That's from last year in pre-AP chemistry. Anytime you see a formula that starts with an H, then you know it's an acid. Okay? Without looking for anything else. All right, so Bronsted-Lowry definition. Is an acid donates a proton in water. What's the charge of a proton? Positive. Okay? An H positive ion, a hydrogen that has become an ion, is a proton. Okay? Because how many electrons does a neutral atom of hydrogen have? 1. So if it gives away that electron, what's the only thing left in the nucleus? A proton. Okay? Because the hydrogen does not have a neutron. Okay? So the only thing left in the nucleus is a proton. So this is a proton. Okay? So essentially the definition for the Bronsted-Lowry and the Arrhenius for an acid is the same. Okay, so an H positive is a proton. So if you ever hear about donating a proton, really what we're saying is it's just donating an H positive. Okay. a base accepts the proton and water. So the acid is giving it away, and the base is the one that is accepting it. Okay? Here's why we use this theory. Because if we use this Arrhenius definition, we're stuck with either we're giving away an H plus or we're giving away an OH negative. Okay? Well, that doesn't work because ammonia is a base. Okay? Can I look at that according to this Arrhenius definition and say that that's a base? No. I would have to use the Bronsted-Lowry. How do I know this? Because if I add an H positive to this, okay, what am I going to get? An H4 positive, which is what? You should know this from last year. It's a polyatomic ion.
Ammonia.
This is ammonia. This is
Ammonium.
ammonium. Okay, so this is ammonia. You're going to use ammonia a lot as a base. So go ahead and learn to love it. All right? And this is ammonium. So my acid donates the proton to ammonia, which is the base. Does everybody see that? All right. So this is the main one that you need to know. Then we have our Lewis definition. In our Lewis definition, and we're not going to do this till the end, so we're just going to briefly go over it, and then we'll work with this more when we get towards the end of the notes. The acid accepts an electron pair, and the base donates an electron pair. Now, the reason why we do like the Lewis definition is the Lewis definition can be used to explain all acids and bases with no exceptions. It works for all of these, so then we don't have to worry about it. So we'll do our same example here. We'll draw it out. Here's how you would draw the structural formula for an ammonia. And then we have this positive hydrogen. So this positive hydrogen has no what? Has no electrons. Whereas this ammonia molecule has an extra what? Has an extra lone pair. Okay? How do we know this is a lone pair?
It's not being shared with anything else.
There you go. It's not being shared with anything else. It belongs solely to the nitrogen. So this positive hydrogen becomes attracted to these electrons because this is positive and these electrons are what? Negative. And we know that opposites attract. Right? So they become, so this hydrogen is going to attach on, okay, to this ammonia molecule, and then what we get is the ammonium. We've got to put that in brackets and show that it is now positive. So who donated the electron pair? NH3, my ammonia. So that means my ammonia is the base, right? Who accepted the electron pair? The H positive. So that means that was my acid. Do we see this? We've got this. Okay, good. So now let's move on to our Bronsted-Lowry because really that's what we care about and that's what we're going to focus on for most of this unit. All right. So, using the Bronsted-Lowry concept of acids and bases, you should be able to write a weak acid-base dissociation equation. What does dissociation mean? We're just breaking it apart. It's dissolving in water. Okay? So when you see this, hopeful, I'm not sure if you've done this yet or not. So dissociation just means we're taking the molecule and we're breaking it apart. Okay? Then you should be able to identify the acid, the base, the conjugate acid, and the conjugate base. If they ask you to do this on the AP exam, please write out acid, base, conjugate acid, and conjugate base. Now when you're doing work in class, we'll abbreviate. We'll use an A for acid, we'll use a B for base, we'll use a CA for conjugate acid, and we'll use the CB for conjugate base. Okay? Because nobody wants to write those words out 1,000 times when you're working these problems. However, when you're on the AP exam, make sure you write it out. Okay, so there's no confusion. So some old person grading your exam doesn't decide to not give you credit because they're going to pretend like they don't know what CB stands for. All right. So a conjugate acid-base pair. Okay, the compounds differ by the presence of one hydrogen unit. So what do we mean? We mean, it's better if you can just see the example here, and it's already done for you, but you need to be able to see it. So we have HNO3 and we have H2. Now looking at this, I should be able to automatically identify the acid. Okay, the acid is right here, HNO3, nitric acid. How can I automatically identify this as the acid? Because the H is in front, so I can go ahead and label that acid. Okay, what happened in this reaction, in this chemical reaction? What happened?
The N moved.
The N moved? Oh, this should be H2O, by the way. Sorry, there's a typo. It should be H2O, not H2.
See, that's what threw me
Water
off.
Yeah.
accepted the hydrogen.
Okay, water accepted the hydrogen. So I donated a hydrogen to here. Okay, according to our Bronsted-Lewis theory, let's come back up here. Okay, who donates the proton? The acid. Who accepts the proton? The base. So that's how I know my HNO3 is my acid, my H2O is my base. Okay. Now that my water has accepted this hydrogen, it now becomes the conjugate acid because now it has an extra hydrogen. Okay. And since my acid lost the hydrogen, this NO3 negative now becomes the conjugate base. Do we see this? Tell me to stop if we don't see this. Okay, we see it. All right. So, also, notice, what does the law of conservation of matter state?
Matter can neither be created nor destroyed.
It cannot be created nor destroyed. It can only be what? Transferred or transformed. So here we just transferred the hydrogen. Are the charges the same on each side? Yes. This has no charge, so it's neutral. This one has no charge, so it's neutral. Okay. Then this one's positive and this one's negative, so these charges do what? Cancel, and so this side is still what? Neutral. Do we see that? Okay. So make sure when you are doing this, if your charges do not stay the same on both sides, then we did something wrong. Okay. Alright, so now let's look at the next one. And again, I know it's already done for you, but you still need to be able to see what's happening here. So, my NH4 positive is my acid, my H2O is my base. How can I prove that? What happened in this reaction? H2O gained a hydrogen, which means it came from who? NH4 positive, and this is called what? Ammonium, right? So my ammonium donated a hydrogen to my H2O. So whoever donates is the acid. Whoever accepts the hydrogen is the base. Right. So now my H2O becomes H3O positive. Okay? So since it accepted the hydrogen, my base now becomes my conjugate acid. Okay? And since my acid gave away a hydrogen, it now becomes my conjugate base. Thank y'all. Alright, so let's look at the third example. So here we have H2PO4 negative. Notice I've got a charge here now, so I've got to make sure that my charges balance out. And I've got my H2O. What's happening in this reaction? My H2O gains a hydrogen from who? H2PO4 negative. So this one's donating its hydrogen. So now that my acid lost a hydrogen, my HPO4 Now, since it lost that positive hydrogen, what's happened to this charge? It becomes more negative. So here it was a -1. Now over here, it's a -2 because it lost that positive hydrogen. Do we see that? Yes. And it became my conjugate base. Since my water accepted the hydrogen, now instead of a base, it becomes my conjugate acid. Okay? And again, because it accepted that positive hydrogen, the charge here now is positive. Okay? So let's look at the overall charge on my reactant side. What's the charge of this molecule? -1. What about this one? 0. So my overall charge on my reactant side is -1. Okay? So now let's look at the product side. What's the charge of this molecule?
+1.
+1. What's the charge of this molecule? -2. So the overall charge on this side is -1.
Is that how you know, like, if we're doing these equations, if it's like messed up, if both of them are the same?
Yes. Right. So if you do this in class, because there's, like in your assignment today, you're going to have to, like, I'll give you this, and you're going to have to break it apart. Okay? So check and make sure your charges are the same. Because if they're not, then you didn't do something right.
So usually, it's gonna be opposite on the other side, like the HCPO or negative is gonna, since it's an acid, it's just gonna be a base on the other side.
Yes.
Like every time it's like that.
Every time. The acid becomes the conjugate base, and the base becomes the conjugate acid. Every time.
And if there's any exceptions.
Yeah, that's good. Ask. I like it.
So,
Yes.
they can't hear you. They can't hear you if you say this and these. So
Yeah.
when you're talking, because you'll say which is this molecule, and you won't mark anything, and they can't see you pointing.
So I need to make sure I'm putting a dot when I say this and these. My apologies, hopeful. I'll start putting dots. So you can see the molecule I'm pointing to. My bad. Alright, so notice in each of the examples before that we just did, I'll scroll back down, I shouldn't have swapped, okay, that we always formed what? H3O positive, okay? In each of those examples that we always formed H3O positive. Okay, H3O positive is called a hydronium ion, and you need to know that, okay? So make sure that you know that. H3O positive is a hydronium ion. Anytime I see an H3O positive or a hydronium ion, then I know the resulting solution is acidic. Okay? Sometimes you'll see that we take out the H3O positive and we'll just put an H positive instead of H3O positive. They're interchangeable. Okay? They're the same thing. So if you see H positive or if you see H3O positive, you know that the solution is acidic. Alright, all a hydronium ion is that we had a water. Okay, there's my water molecule. Okay, because oxygen has these lone pairs, okay, it makes my oxygen slightly what? Slightly negative. Okay? It makes my oxygen slightly negative. Remember the little half S symbol? Okay, that means slightly. So it makes my oxygen slightly negative. So if there's an extra H plus around, okay, there's an extra H plus around, it becomes attracted to that negative oxygen. Because again, opposites do what? Attract. So when it becomes attracted to this oxygen, that's when we get, and it would only have one lone pair then, this H3O positive. So that's how it forms. Do we see this? Okay, all right. So an example of this happening, okay, here I have H2O. Then we come in and we add HCl. Which one of these is my acid? HCl. How do I know that this is my acid? It starts with an H. Okay. How else would I be able to tell that this is the acid? There you go. Over here, I see that it gave away its hydrogen to this water, which means this is the acid, and in this case, water becomes my base. So what happens is, what ion is this right here? Hydronium. My hydronium is now my what? Conjugate acid. And my Cl negative is now my conjugate base. Do you see this? One of the questions, and I'll show you another example of this when we get later on in the notes, they've really gone towards, and you had a question like this in pre-AP actually last year. You don't remember, but you did. One of the things that they'll like to do now is they'll like to give you like a drawing like this and ask you like which hydrogen is going to be donated, okay? Or which hydrogen is going to dissociate. And you'll see when we get on, like this doesn't look complicated. There's only one hydrogen, so hopefully you would just know to circle that one, right?
Oh. It was the closest one to it, right? In the question last year, I think I remember it.
You think you remember it? We'll see. I'll show you the example that you did last year on your test in just a few minutes. So, but when we get to other examples, you'll see where it's a little bit more difficult. One key sign to know which hydrogen is going to be donatable is when you have all of these lone pairs. Because these lone pairs means that this chlorine, right, is hogging, essentially. That's not a very scientific term, but that's what we're going to go with, okay? It's pulling more of the electrons towards it. Because if you look on the periodic table, I can't fix that. We're just going to go with it, right? If you look on the periodic table, all right, chlorine is in group what? 17. Hydrogen's all the way over here in group 1. What happens to my electronegativity? Do we remember this from last year? What is electronegativity?
The amount it like bonds or something.
The desire to what?
Gain electrons.
There you go.
I was kind of cool.
The desire to gain an electron. So as I go across the periodic table, what happens to my electronegativity?
It gets increased.
It increases. So chlorine is much more, this chlorine is much more electronegative than the hydrogen. So when they bond together, chlorine wants the electrons more than hydrogen, so what's it going to do?
Get the electrons.
Pull those electrons toward. There you go. It's going to get the electrons. It's going to pull the electrons towards it. So it makes it very easy to pick this hydrogen off, okay? Because it's not getting any of the goods anyway, all right? Chlorine's being a hog. It's being like that friend, you know? It just always gets, never gives, you know? Just never, all right? So that's where we're going here. All right, notice in all of these examples that we did back here, my water was a what? Base. In all of these examples, water was a base. Water is what we call an amphoteric compound. We'll go over that in just a second. Where water can act as an acid or a base. So if I look in this example, I see that my water has now become a what? Acid. Okay? I think this is in your notes later on, but we'll go ahead and write the word, just so you can remember it. Water is amphoteric. Okay. And all that means is that water can act as a base or it can act as an acid. Either or. No big deal. Alright, so here, first of all, if you ever see ammonia, NH3, you know that's a base. It's the most common base we use. Alright, but I know this is a base, but how could I tell, alright, let's just pretend I don't know, alright, how could I tell that my NH3 is my base and my H2O is my acid?
NH3 receives the electrons for the hydrogen.
Here you go. My H2O is giving its hydrogen to NH3. So whoever does the donating of the proton is the what? Acid. My NH3 is accepting the proton, so it is the base. So now my NH3 becomes NH4, so it changes from a base to the conjugate acid. My H2O, that was an acid, changes to OH negative, so it is now the conjugate base. Do we see this? Yes. All right, so we look at the next two. What's happening in this equation? Okay. Water is donating a hydrogen to CO3 negative, so that makes my CO3 negative the base, and it makes my H2O the acid. So now that CO3 negative gained the positive hydrogen, what's happened to my charge here? It became more what? More positive. Because here it was 2 negative, then I gained a positive hydrogen, so now I just become -1. Do we see that? Okay. And so what was once my base now becomes my conjugate acid, and what was once my acid now becomes my conjugate base. Okay. Same thing in this example. Water gives its hydrogen to my phosphate ion. So now my phosphate ion, that was the base, gains the hydrogen. So since it's positive, that 3 negative becomes a 2 negative. And my base now becomes the conjugate acid. My water that was an acid gave away that positive hydrogen. So now it becomes OH negative and the conjugate base. Notice in all of these examples, we formed OH negative. Anytime I see that I formed OH negative, I know that it is alkaline, or another word that we use for alkaline is basic. These are equal terms. You will not be penalized if you say alkaline or basic. They both mean the same thing. All right. So, let us try. Exercise 1. In the following reaction, identify the acid on the left and its conjugate base on the right. Similarly, identify the base on the left and its conjugate acid on the right. So all we're doing is identifying acid, base, conjugate base. Easy to do, right? So here we have HBr, hydrobromic acid, plus ammonia goes to ammonium plus a bromide ion. You try it on your own right quick. Label. I'll give you a minute. I had a worksheet for us to do today, but at this rate, I don't know if we're going to get there. This is taking longer than I thought. I know, you're so disappointed, Spencer. You're not going to get to do your worksheet. All right, so what's happening in this equation? Oh, sorry, guys. Here we go. All right, what's happening in this equation? Excellent. My HBr is donating a hydrogen to my ammonia. That means my HBr is the acid. My ammonia is the base. Okay. Now that my NH3 has gained a hydrogen, my ammonium is now my what? Conjugate acid. And since my HBr has lost this hydrogen and now become Br negative, this is my conjugate base. Pretty simple, right? Okay. This shouldn't be difficult so far. We should be liking it. Okay. This is stuff we like in AP chemistry because we get it. All right. So B says, what is the conjugate base of H2S? What is the
Yes.
conjugate base of H2S? Okay? What becomes the conjugate base? Let's talk about that.
Yeah.
The acid. So that means this is an acid. Okay? There you go. So what does the acid do in the chemical equation? It donates the hydrogen. So this is going to get rid of an H plus. So what is it going to become? HS, and excellent, Jana. It's going to be negative. Ow! Right? It's going to be negative. We see that? Alright. So let's try C. What is the conjugate acid of NO3 negative? HNO3. Okay? What becomes the conjugate acid? The base, right? So I know this is the base, right? What does the base do in the chemical reaction? It accepts the hydrogen, so it's going to accept the hydrogen. So this was negative, now it's accepting a positive, so the molecule we get should be what? Neutral. Okay, it shouldn't have any charge. We good? Questions so far? I feel like this is the best we've done all year. I'm excited.
Yeah, so
Can we just take a test on
That'd be
this?
right working from yesterday.
I honestly, looking at the time, because I didn't plan on lecturing all day today at all, but I don't know if we'll get to the worksheet. But the worksheet is pretty simple, and I designed it essentially to bring up those quiz grades from yesterday. That works. I think, did anybody make a 10 out of 10 yesterday? No? Anybody make an 8 out of 10?
Oh.
I should have made.
So we'll
6 out
add
of
2
10.
points to
I
everything.
picked the wrong
2
one.
points, we like 2.
Yeah, like 20.
So that's a 20. 20 points.
I should have had it.
So I have a 60.
Okay.
We're passing, I
I should have had a 60. Then it makes you an 80.
Alright, guys, back to this. Excuse me. Back to this. Alright, now, so far, we've only worked, I'm up here. We've only worked with acids that donate 1 proton, but this is not true, okay? Acids can donate more than 1 proton. So, we have 3 different types of acids. The first one is a monoprotic. What does mono mean?
Who knows?
1, okay? So, how many hydrogens is this acid going to donate? 1. It's only going to donate 1 hydrogen. So, you see here, C2H3O2. That was a polyatomic ion you were supposed to memorize last year. What's it called? Acetate. Okay. Excuse me. It is acetate. All right. When we add a hydrogen, okay, the 8 becomes what? Ick. Okay. The 8 becomes ick. So this is acetic acid. Okay. Acetic acid is the main component in what? Vinegar. Baking soda would be a base, so it doesn't have acetic acid in it. Alright. Okay, diprotic acids. Di means what? 2. So how many hydrogens can a diprotic acid donate? 2. Now, it is not going to donate both of these hydrogens at the same time. Okay? It's only going to get rid of 1 at a time. So here we have H2C2O4. Okay? So the first reaction, it would get rid of the first hydrogen and it would become HC2O4. What's my charge going to be? Negative, because I got rid of a hydrogen. Then it can go through a second reaction where it can give away this next hydrogen and become C2O4. What should my charge be? 2 negative. Yes?
So after the first reaction, would it still become a conjugate base?
Yes. It would. Because you would have to treat them as 2 totally separate reactions. Like if I was to write this out, I would have to write it out in 2 different equations. Like the first equation would be H2C2O4 plus, let's just say water, I guess. goes back and forth, and I'm going to say that this donates to this, right? So I get H3O positive plus HC2O4 negative. Okay? Then I would come back and I would completely rewrite the equation and say, well, HC2O4 plus water again, because it's only going to be able to react with the water. It can't react with this hydronium ion. Okay? Goes back and forth to C2O4, 2 negative, plus H3O positive. That makes sense? So it's two totally separate reactions. You can't treat it as the same reaction. And then we have polyprotic. Poly just means what? Many. Okay? Poly just means many. So essentially, polyprotic acids are just ones that can donate 3 or more. And really, you'll never deal with more than 3. In AP chemistry, this what they call the scope of AP chemistry normally doesn't go past diprotic. Okay? But we will look at the polyprotic. Alright? PO4 is what polyatomic ion? Phosphate. When we make it an acid by adding the hydrogens, my 8 becomes a what? Ic. So this is phosphoric acid. I don't know the name of this one, obviously, because I skipped it. And again, it's not just going to dump all 3 of its hydrogens at the same time. Okay? That doesn't happen. Right? It would dump the first hydrogen first and become H2PO4. What's my charge here going to be? Negative, because I got rid of 1 hydrogen. Then I can get rid of the other hydrogen and become HPO4. My charge should be, there you go, 2 negative. And then I could dump that hydrogen, that last one, and become PO4, and my charge should be 3. And again, this would happen in 3 separate reactions. It wouldn't happen all at once. We can't just put them in solution and just start dumping all 3 of them at the same time. All right. Polyprotic bases, again, poly just means many, okay, can accept more than 1 hydrogen, okay, like we just said here. Once I lose the hydrogens, this PO4 3 negative became my what? Conjugate base, right? Because it lost the hydrogen, so this is my conjugate base. So what does a base do? Accepts hydrogens. It receives hydrogens. So I could start adding the hydrogens back on. Okay? And how many hydrogens total could this accept? 3. How do I know, if I hadn't just went over all of this, how would I know that this PO4 3 negative can accept 3 hydrogens? There you go. It's a -3 charge, and it wants to be what? Neutral. 0. Alright, next page. Here we go. Here's the amphoteric. You don't really see the amphiprotic, but you see amphoteric a lot. And these are your molecules that can be either acids or bases. And the most common example that we have of this is water. Okay? And also, anions of weak acid, like in the example we had above, when we had HPO4 2 negative. Okay? This can be an acid or a base, correct? It has this hydrogen here that it can what? Give away. But because of this 2 negative charge, it can also what? Accept. Do we see that? So it's amphoteric. Alright, the answers to A, B, C, D, and E are on your notes, and it is on your notes on purpose so we can make sure that we do it correctly, but you still have to know how to do this. Okay, so let's make sure we pay attention. and we understand it. It says write the simple dissociation, and another word of this is ionization, because when we break the molecules apart, what are we creating? Ions. And what are ions?
Charge particles.
Charged particles. Excellent. We're getting somewhere today. Okay, and then notice it says omitting water. Okay, a lot of times when we write our chemical equations, we'll just take water out of the equation. All right, we know it's there, we're assuming that it's there, but we just omit it and we don't write it. So, A says hydrochloric acid, and then it went ahead and was nice and sweet to you and gave you the formula HCl. So, if I take HCl, how would I write that breaking apart? What two ions is it going to break apart into?
H positive and Cl negative.
There we go. H positive plus Cl negative. And let's go ahead and put our aqueous symbols. Because the aqueous lets us know that it's what?
Aqueous.
It's dissociated in
Water.
water. Okay? Now, what do they mean by omitting water? If we would have wrote this the other way, we would have said HCl plus H2O. Okay? Goes back and forth. This is my acid, so it's going to donate my hydrogen to the water. So my products would be H3O positive and Cl negative. Okay? This equation and this equation are considered to be equal to one another. Okay? Because remember, we said we can use this hydronium ion and H positive interchangeably. They're the same thing. Okay? So all we did here is we just took water out of the equation. Alright, so acetic acid. How are we going to show acetic acid dissociating? So first, we start with writing the acid. What is this going to dissociate into?
H positive and C2H3O2.
Excellent. I wrote an O. It's supposed to be an H. What's this ion called?
Acetate.
Acetate. Thank you. All right, now we're going to show ammonium dissociating. Now remember, when an acid dissociates, all right? When an acid dissociates, all it's doing is losing a what? Losing a hydrogen ion. So we should always show that H plus there. And then what's my other product going to be? NH3. Is there going to be a charge on this NH3? No. It was positive. My ammonium was positive. It lost the hydrogen. So now my ammonia is neutral. All right, the aniline ion. The fancy one. C6H5NH3. And don't forget, I know it may be hard to see on your paper, that is a positive there. Alright, quick hint. What if they ask you you have the answers there so you know, but if they asked you this on the test, where is the hydrogen going to come from? Circle the hydrogen that's going to dissociate. It's going to come from this NH3, okay? Anytime you see hydrogens written after carbons, they are not going anywhere, okay? Hydrogens are going to stick with the carbons. So here where we have the C6H5, that means these 5 hydrogens right here are bonded to this carbon. That's why they wrote it like that, okay? Instead of writing C6H8N, okay, they specifically wrote it C6H5N and then stuck these hydrogens on the end, these 3 hydrogens here on the end. Because these 5 hydrogens aren't going anywhere. They're sticking with carbon. So when I write this dissociating, I want to make sure that I take away my hydrogen from my ammonia group. Is there going to be a charge here? Nope. And then, of course, I should have an H positive that came off. And then E, we have the hydrated aluminum 3 ion. We've got Al, H2O6, 3 positive. And when we write this H2O bonded to this aluminum like this, remember that means it's actually attached to the aluminum. Okay? So it's an aluminum and it's got 6 water molecules coming off of it. One, two, three, four, five. So where's my hydrogen going to come from? One of the waters, right? So just pick a water. I'm going to choose that one. All right. So let's say my hydrogen's going to come off of here. So no, I'm going to have an H positive. Right. So now, how many whole water molecules am I going to be left with? 5. 1, 2, 3, 4, 5. So I'm going to write my aluminum with the H2O 5. What's left over on this water molecule after I take away one of these hydrogens?
One H, OH negative.
It's an OH, right? Okay, and you're right. OH has what charge? Negative. So since OH has a negative charge, this 3 positive is going to become a what? 2. Or, essentially, because I lost a positive, it becomes 2 positive. Do we see this? Yes. All right. This is where things get, it's not difficult. I promise it's not difficult. It's really not. I don't think it's difficult. But sometimes it's a hard concept for us to wrap our brains around because it's not what we associate as strong and weak. Okay? Let me go get my example.
Is it so right here?
Okay, we're going to do an example before we get started with this. Ace, you want to make sure I'm doing this right? Sorry, Hopeful, I'm still learning. Okay, so I want to go to webcam. So I just click on webcam
Then unclick monitor.
and unclick monitor.
See 1 second.
Oh, I may not have started it yet.
You may not need to. I wonder. Let's make sure it's captured from the webcam. It is.
Alright, hang on 1 second, guys. We're trying to figure out the camera.
I wonder. Go ahead and record it on here and see.
It's like here. They didn't change it. Should I just stop it and then do the demo on a separate video?
Go ahead and do that.
Alright, excuse me, guys. I know it's different. Just hold tight. Alright, Hopeful, we're going to stop the recording and we're going to make a new video of the demo and then I'll pick up with the notes in a second video. Okay? Yay.